Hello everyone, welcome to the course on Introduction to Multi-Agent Systems, and this is the first lecture for the course. I am the course instructor Dr. Twinkle Tripathi. So let's get started. So before we get into the technical definitions and contents, let's start with a very small example of ants. Now, how do ants operate? For example, when they are hunting for food, how do they generally behave with each other in their exploratory processes? So to start with, it is interesting to note that most species of ants have actually little or no sense of smell at all. However, what they can do is only smell things in their vicinity. Of course, with these limited skill sets, ants are supposed to be terrible explorers. However, we already know that ants are everywhere. For example, you can try this at your home. You leave a piece of food somewhere and you leave it for some amount of time. After a while, you see ants gathering around it. So the agents, which are actually supposed to be terrible explorers, are actually everywhere to be seen. Let us see this image on the right. Not only are they everywhere to be seen, the small image shows that there are multiple ants who have formed an ant bridge, which is allowing other ants to walk over from one part to another, as you can see here. So how are ants able to do that? The agents, which are supposed to be terrible explorers, how are they managing to be seen everywhere? The answer to that is cooperation. Now, cooperation is the key which enables ants, which otherwise have very limited skill sets, to achieve tasks which a single ant would not have been able to achieve. An example being the image that we see here. We see that, so this is an animated image, not a real image, but conveys this idea that multiple small ants can actually come together to lift a rock which is much bigger than all of them, which a single ant would not have been able to do. So this is the power of cooperation and multi-agent systems, which allows agents to transcend beyond their own abilities and perform tasks which a single agent would otherwise not have been able to do. Let us see some more examples of multi-agent systems. So the first one is a wireless sensor network, power grids, and swarm of robots. Now, all of these are examples of multi-agent systems, as they consist of smaller entities which are working together or functioning as one unit. So with this, so what have we understood so far is that a multi-agent system is actually a large system which consists of smaller entities which are operating within it. But let us now formally define what is a multi-agent system. So it is simply a group of n entities which are distributed over a network and are trying to achieve some objective in a collective manner. Now, multi-agent systems and their behaviors actually help understand many complex systems and their emergent properties. We'll talk about more specific examples of such systems towards the end of the lecture. Let us get now a bit deeper into the definition. Understanding further, two questions actually arise from this definition. First of all, is there a dynamical aspect that we can attach with a multi-agent system? The second question is, how do we actually put together a collective objective to achieve some task as a team? So we'll again try to answer these questions in this lecture itself. Let's start with the first question. Where is the dynamical aspect in a multi-agent system? To understand that, we will need to first define what are the small autonomous agents or the entities within each multi-agent system. To do that, are the agents actually defined using certain kinematic models. The first kinematic model that we will talk about is a single integrator model. Now, in a single integrator model, let xi, which is written here, denote the state of some ith agent. Now, so before we start with that, let me just draw a system which has multiple agents which are interacting with each other. For example, we saw some images before of multiple drones within the network and power grids. So let us say we have a large network here which consists of many small units which are interacting with each other. Now we are looking at the ith agent here. Let me use a different color to highlight this. Let's look at this ith agent here. Now every ith agent, where I simply belongs to, it is representative of any agent. It lies from 1 to n. Now every agent I in a system, if it can be defined using a model like this, where the input is directly applied to the first derivative of the state, then this becomes a single integrator model. Similarly, we can have a double integrator model where the input is applied at the second derivative of the state. Now, an example of the second derivative could actually be the physics-based models arrived or derived using the Newton's second law, F equals ma. If we write this a bit in a bit more descriptive way, we will get something like this. So we have F, which is the input applied to the system, and the state is this x. So such models which are defined with input appearing at the second derivative simply represent a double integrator model of the agent. Note that while we have said that every agent I here satisfies these properties, in realities, in a large networks, the models of agents could actually be heterogeneous in nature. Now, these are some of the linear models of agents. There are certain models which are also non-linear in nature. Let's take a look at one. Now, the second kind of model that we'll, or rather the third kind of model that we'll look at is a unicycle. What is a unicycle model? Now, a unicycle model consists of, for every agent I, it consists of 3 states associated with it. The first is, let's draw this. Suppose this is the ith agent here. Now, we have some angle here, alpha, which we will call as the heading angle. What is the heading angle? Let us say this vector here is the velocity vector of the agent, then the angle which the velocity vector makes with the reference is known as the heading angle, and x and y obviously are simply the Cartesian position coordinates. And omega is simply the angular rate. Okay. Now, such systems actually are non-linear in nature because of the involvement of the terms cos and sine in them, and are slightly more difficult to analyze than the linear counterparts like the single integrator and the double integrator model, which we talked about before. Let us see an image of some real world systems which are actually described using the unicycle model. The first one is simply, obviously, as the name suggests, a unicycle. Now, the point mass version of this. Now, if you look at any wheel, the wheel cannot translate laterally. It can only move forward like this, meaning the wheel, the point mass actually has a velocity vector along which it moves, and it does not translate laterally. So, wheel is actually a perfect representation of the unicycle model. Now, another example of it would be any wheeled system like the car which is shown here. Note that several other systems can also be represented using unicycle models like a fixed wing aircraft, and even submarines. Anything which has a velocity vector and does not translate laterally can be used or can be represented using a unicycle model. So these are some of the most commonly used models in multi-agent systems. So what we have understood so far is we have a multi-agent system, we have some n number of entities in them, and every entity I can be modeled using any one of these models. So meaning the system can actually be homogeneous or heterogeneous in terms of the models that are being used to represent the entities. Okay, so we understood that there are some entities in the network. Now let us try to understand how should these entities act together so that they can put in a collective effort to achieve some team objective. Let's try to answer that question. In order to answer that question, let us start with a very interesting video which represents a flocking behavior among birds. So the video that we are just going to watch represents the murmuration of the birds, starlings. So let us see what all of them, when they combine together, what they can do. So the video starts with some birds which are scattered across, and then we see that very interesting shapes arise through the collective motion of the birds. So what exactly happens in the video? We see that those birds actually, through their collective motion, give rise to very interesting shapes in the sky. So now many questions arise, how do they manage to do it? Now the formation sometimes can be really large. So how do the birds still manage to communicate with each other so that such interesting shapes arise? We'll try to answer that question through a simpler behavior, which is simply the V-shape formation that arises among birds. Now V-shape formation is something that almost everyone must have seen at least once in their lives. So we see that a group of birds are flying together and their heading angles are actually aligned. All of them are pointing in the same direction, giving rise to a V-shape formation. And you see the agent that is here is actually quite far away from this agent. Sometimes these formations can even be as far wide as a kilometer or something. How do the birds still manage to achieve a global formation? Now to answer this question, Craig Reynolds in 1987 proposed the Boyd's model, which emulates this behavior by proposing a model for it. So what exactly is the Boyd's model? Now the term Boyd simply means bird plus oid, where oid means, so it means a bird-like entity. So the Boyd's model attempts to capture the way the entities or birds align themselves in swarms, and each Boyd interacts only with its neighbors following just three simple rules. So what are those rules? The first rule is separation, meaning every Boyd should move in such a manner that they do not collide with each other. It does not collide with any other entity. The second rule is alignment, where every Boyd or entity must move in such a manner that it aligns itself along its neighbors, which is the second aspect. And the third part is cohesion. In cohesion, it says that none of the agents should actually wander away from the group, meaning the first rule tries to take them a little bit far apart so that they do not collide with each other. And the second rule makes sure that they're all moving in one direction. And the third rule tries to make sure that while they are avoiding collision, they still do not move too far away from each other. So what exactly happens when we take a set of n agents together who are using the Boyd's model and doing a certain motion, does a collective behavior arise? Now, to answer that question, we will watch this video. So, we see that there are a lot of entities in this video, and all of them are trying to follow the Boyd's model. And eventually, we see that the group which was initially scattered has now almost come together, resulting in some sort of a global formation. So, now let us ask ourselves that question. We saw that the Boyd's model simply gives us very simple rules that the agents can follow to achieve some group objective. What is a group objective? It simply means that all of them are working as just one unit to achieve some common task. So, the question is, where exactly is the dynamical aspect here? Now, notice that every Boyd has its velocity vector and cannot really translate laterally. Now, this actually affects their paths, their motions, and since it affects the paths of each of the motions, it also eventually affects the paths of the overall flock. So, meaning every individual affects the group, resulting in a networked system first of all, and they all have constraints in terms of how they can move, meaning their motions are actually governed by some dynamical models, giving rise to the second term, dynamical. So, meaning the entire system put together acts like a networked dynamical system. So, this brings me to the last slide of the lecture. So, I'll end this lecture by actually asking some questions to all of the students who are watching this. So, there are several key questions that we will try to answer in this course. The first one being, now we have the set of agents which are acting together to achieve some common task, but how exactly are they talking to each other? Meaning, how do we express their interaction topology? How do we analyze the emergent collective behaviors of the overall network dynamical system? So, I encourage students to actually think about this. We saw earlier the Boyd's model and we saw what interesting shapes can arise. So, what exactly does the Boyd's model do to ensure such a nice behavior? So, this is something all the students are encouraged to think about. The third question is, suppose one part of it is to have an object, have some simple rules and then observe what is the emergent behavior. But sometimes when we are solving practical real world problems, we could actually have some desired global objectives in mind already. So, now once we already have a desired global behavior, how do we ensure that such behaviors can be enforced by the system? And the last part is, are there any restrictions on what the network topology should look like? Like, does it really play a role in ensuring these collective behaviors? Or to put it simply, how do we choose a network topology that allows us to achieve a desired emergent behavior? If we are unable to choose the network topology, can we always have a suitable control input that can allow us to achieve a desired emergent behavior? So, let me pause the lecture today with these questions in mind. So, I encourage the students to think about it and try to apply this to the practical systems that they have seen, like a flock of birds is something I am sure a lot of us have already seen before. So, please try to answer these questions for that flocking behavior. So, these are the references that we used for today's slides, and thank you.